So welcome to the last session of today. The first talk is about succinct vector, polynomial, and functional commitments from lattices by Ho-Taek Wee and David Wu, and David will give the talk.
All right, so thanks a lot for the introduction, and thanks everyone for coming to the final session of the conference. So I'll be telling you about succinct functional commitments from lattices, and this is joint work with Ho-Taek. So in a functional commitment, a user can commit to some input x and produce some commitment sigma, and later on, they can take their commitment sigma and open it with respect to some arbitrary function f to the value f of x. More formally, and in this talk, we're going to focus exclusively on non-interactive commitment schemes, where the commitment algorithm and the opening algorithm will take as input an additional common reference string. So the commitment will take the common reference string, or the CRS, takes in the input x, and produces the commitment and some commitment state. Later on, when you want to open a commitment, you specify a function f, and that produces an opening, which I will denote pi. Finally, you can verify the commitment, and the verification algorithm takes the commitment, takes a function f and a purported value, and checks that the value is actually f evaluated on the underlying commitment itself. The main security notion that we're going to consider in this talk is binding, which essentially says that a computationally bounded or efficient adversary should not be able to open the same commitment to two different values with respect to the same function. So namely, once I've chosen a commitment and a function, there's only one possible value that you can open to. You should not be able to find two possible values for the same commitment function pair. We can also require hiding properties, which says that the commitment and the opening actually hides all information about x other than what is revealed by f of x. I'm not going to dwell too much on this in this talk. The main requirement in terms of for a functional commitment, though, is the efficiency requirement. In particular, we require that both the commitment and the openings be short or succinct. In particular, what succinctness means in the context of the commitment is that the length of the commitment should be polylogarithmic in the length of the input. The commitment must compress the input itself. It can also depend polynomially on the security parameter lambda. Similarly, we require that the openings also be short, namely they should also be polylogarithmic in the length of the input, but we do allow them to scale with the length of the output. So functional commitments are generalizations of notions that you may have encountered, such as vector commitments and polynomial commitments. These are notions that have received extensive study due to their implications and applications to constructing succinct arguments. So in a vector commitment is basically a functional commitment where you open to a specific index of a committed vector. And a polynomial commitment corresponds to the special case where you commit to the coefficients of a polynomial and then open to the evaluation of the polynomial at a particular point. Functional commitments, and specifically its specializations to vector commitments and polynomial commitments, have received extensive study over the years, starting from Merkel's classic construction of a vector commitment from collision-resistant hash functions. There has since been a long line of constructions studying new instantiations based on algebraic assumptions, either pairing-based assumptions, group-based assumptions, factoring-based assumptions, and even lattice-based assumptions recently. If we consider the generalization to functional commitments for arbitrary functions, so namely any function computable by, let's say, a Boolean circuit, essentially the feasibility result follows from any collision-resistant hash function and a succinct non-interactive argument. However, if you look at this construction, it leaves more to be desired, namely the reliance on succinct non-interactive arguments typical for MP typically brings in non-falsifiable assumptions and also relies on non-black box use of cryptography. So a natural question that you might ask is, can we construct functional commitments for broad classes of functionalities without bringing in non-black box use of crypto and without needing non-falsifiable assumptions? There has recently been several works that have made progress on this for the case of linear functions in a very nice construction by Albrecht et al. From Crypto last year for constant degree polynomials. The latter construction relies on new assumption on ideal lattices, but importantly, this is a falsifiable assumption. What we focus on in this work is a new framework for constructing functional commitments from lattice-based assumptions. And as a starting point, we show a new vector commitment scheme based on a standard short integer solutions assumption. And notably, our construction has several appealing properties that essentially follows for free from our framework itself. So for instance, we get hiding properties. We can commit to large values. This will become more apparent later on. And similar to previous works, our construction also is linearly homomorphic. But I think what is more interesting is that our framework readily generalizes beyond vector commitments and actually gives us functional commitments for all bounded depth Boolean circuits. Here, the price that we pay, however, is we rely on a new kind of assumption, a new falsifiable assumption. I view it as a Q-type generalization of this SIS assumption. So this is something that we call the structured basis assumption, which I will introduce later on in this work, in this talk. Finally, I'll remark that the structured basis assumption that we rely on actually is less structured than a previous assumption by Albrecht et al. Used for constructing functional commitments for constant degree polynomials. I'll also mention that this is an area that has received a lot of growing interest in recent times, and there are actually two concurrent works that I want to call out, who also give lattice-based functional commitments for Boolean circuits. A very nice construction by Balbas, Catalano, Fiore, and Lai show how to construct both pairing-based and lattice-based functional commitments for Boolean circuits, which achieves short openings and also supports fast verification in a preprocessing model. Their constructions, at least in the lattice setting, rely on a new falsifiable assumption on module lattices. Earlier in this conference, we saw the work of De Castro and Pikert, who show how to construct a functional commitment for all circuits that has a transparent setup, so a public coin setup, and only relies on standard assumptions, namely the short integer solutions assumption. The drawback of their work is that the openings are not succinct. They do not satisfy the succinct opening property I defined earlier in this talk. Okay. All right, so what I want to focus on, though, today is introducing our framework for constructing lattice-based functional commitments. So I'll start with a framework that shows how to get vector commitments, and then how to extend it directly to get to functional commitments. One nice property of our framework is it captures and also generalizes previous lattice-based functional commitment schemes. So what do these existing lattice-based functional commitment schemes look like? Suppose I want to commit to an input of length L. And you can think about these inputs as binary valued, or they can be taken from a small field. So the common reference string in all of these constructions is going to consist of a sequence of L matrices, one associated with each bit of the input, as well as L target vectors, again, one associated with each bit of the input. For the description here, we don't need to worry about the distribution of these matrices or vectors. This is just the structure that we care about. The important component is this auxiliary data. And the auxiliary data is essentially a way to recode the ith matrix to the jth target vector. So in particular, I'm going to give out short vectors uij that takes ai times uij is equal to tj. So it's a way to send something from the ith component onto the vector associated with the jth component. And critically for these constructions, I'm only going to give out these components for I not equal j. So essentially, you can view them as cross terms, if you will. So once I have this common reference string, what is the structure of a commitment? It's simply a linear combination of the target vectors. I take a linear combination where the coefficients correspond to my input. To open to a particular value y at a particular index I, so again, I'm only talking about vector commitments, so I'm only interested in opening at a particular index. What I do is I give you a short vi such that the commitment satisfies this verification invariant. It's the purported value times the ith target plus the ith matrix times the opening. So which target and which matrix I use depends on the index that I am opening to. So the question then is, how do you construct such an opening? Here, you are going to use this auxiliary data. The opening to a particular index is going to be a linear combination of the recoding vectors uij. Basically, I'm going to take a linear combination that allows me to recode AI to all of the tj's for the other components in my commitment. So to verify that this is actually correct, we can start with the main commitment relation, which is the sum of the xi ti's for all I. We have one component, which is the component that I'm opening to. And then I have a bunch of these cross terms, which are the form xj times tj. And I want to get this into the form of ai times something short. Well, how do I do that? That's exactly using the recoding components I'm giving out in a CRS. So if this relation will hold, as long as the input x is short. So in previous instantiations, the construction of Pikert, Pepin, and Sharp consider the setting where the matrices A and the target vectors are uniformly random. It turns out that this suffices to give you a vector commitment from the standard short integer solutions assumption. The Albrecht et al. Construction from Crypto last year consider an instantiation where the matrix and the targets are structured, and this turns out to be sufficient to give a functional commitment that allows you to open to arbitrary constant degree polynomials based on an ideal lattice assumption. Now let me tell you about our approach. Our approach actually starts at the very end of the previous description. I'm going to instead take a look at the verification invariant. The verification invariant says that for each index I, this relation here should hold. Right? The commitment is equal to AI times the opening VI plus XI times TI. And this should hold for all of the indices in my vector. So what I can do is I can rewrite these L equations as actually a single linear system where each row basically corresponds to one of these invariants. Row 1 corresponds to opening for component 1. Row 2 corresponds to opening to component 2, and so on. So why is this useful? So before I tell you why it's useful, I need to do one more thing. I need to rewrite the commitment C. I'm going to actually decompose it into the gadget that is powers of 2 matrix multiplied by the binary decomposition of C hat. I'm just going to make a substitution. I'm going to write C as G times C hat, where G is this gadget matrix here, and C hat is just the binary decomposition of what used to be my commitment. So again, I have done nothing fancy. I've just rewritten this linear relation. I have a new linear system that describes what the commitment and all of the openings should satisfy. So if we look at these previous constructions of functional commitments, basically what is given out are the matrices A1 up to AL, and as well as these target vectors T1 up to TL, and then there's these cross terms auxiliary components. This is where our framework differs from those of prior work. Instead of giving you these auxiliary data, we're going to actually replace it by giving out a full trapdoor for the matrix B sub L. So the matrix defined on the right here. What I mean when I say a full trapdoor, I mean a trapdoor that allows for an efficient algorithm to actually sample short solutions to a linear system defined by BL. In particular, what that means is for any target vector on the right here, I can actually sample a short solution, V1 up to VL and C hat, that satisfies this linear system. So what that means is now to commit to an input X, I'm not going to use the deterministic algorithm of taking linear combinations as before. I'm simply going to sample a solution to the linear system. So instead of constructing the commitment and the openings independently, now I'm going to do a joint sampling and compute them together. So I'm going to specify the targets, and then I'll use my trapdoor to jointly sample a V1 up to VL and a C hat that simultaneously satisfies all of these verification invariants. Finally, once I get the C hat, I'll just use my substitution that C is equal to G times C hat. That will be my new commitment. So the advantage of this approach is twofold. So the first thing that you might observe is that nowhere do we now require that the x's be small. We're not taking linear combinations of target vectors or matrices anymore, or linear combinations of short vectors. We're just doing pre-image sampling, and we can target whatever we want on the right-hand side. So it doesn't matter that x is small. We can commit to x as being large. Doesn't affect anything. The second property that we achieve basically for free is because we're jointly sampling the openings and the commitments together, we can directly analyze and characterize the distribution of these pre-images. And in fact, you can actually show that these pre-images actually statistically hide the unopened values. So we get hiding also for free as a corollary of our framework. So the only remaining item I need to describe now is how do we argue that the scheme satisfies binding. Basically, we want to show that well, I guess I won't have time to show it here, but what we can show or argue is that an adversary that breaks the binding property can actually solve the short integer solutions problem with respect to one of these matrices A sub I. So the short integer solutions, if you haven't encountered it before, just says given a random matrix A that's very wide, find a short non-zero solution in the kernel of A. So here, what we're going to do is we're going to formulate or first state an assumption, which we call the basis augmented cis assumption, or basis assumption for short, which essentially asserts that the SIS problem is hard with respect to A sub I, even if I give you a trapdoor for this related matrix B sub L. So notice that if I assume that this assumption holds, then the security of our construction basically follows for free, because because an adversary that breaks binding solves cis with respect to A sub I, given the trapdoor information that I put in the CRS. So at this point, it looks like that we have basically stated an assumption that just allows our scheme to be secure. This is not super interesting. It turns out, though, that when the matrices A1 up to AL are actually sampled uniformly and independently of each other, the basis assumption for this particular configuration actually follows from the standard SIS assumption. This actually follows by standard lattice trapdoor extension techniques, which I won't have time to go into here, but essentially there's a way to simulate the trapdoor for B sub L if you know the trapdoors for all but one of the components and the public trapdoor for the gadget matrix. So to summarize, using our new framework, we directly get vector commitments that support committing to large values. We get private openings for free. And everything still follows from the standard SIS assumption because the basis assumption we need here actually can be reduced to SIS directly. But the more interesting bit is how do we take this framework that I described and actually generalize it to get general purpose functional commitments, not just opening to a single component now, but opening to an arbitrary function evaluated on the input itself. So let's take a look. The starting point here will be the lattice-based homomorphic commitment by Gorbanov, Akuntanathan, and Weeks. So let me briefly remind you how that goes. The construction here will take in a random matrix, an arbitrary matrix A, usually very wide. And the commitment in a Gorbanov, Akuntanathan, and Weeks, or GVW construction has the following structure. We're going to commit to each bit of X individually, and the invariant, or the verification relation, is that I'm going to take xi times g, and I'm going to add to it a times vi. So ci here will be a commitment to the bit xi. And now, using the magic of lattice homomorphic evaluation developed by Gentry, Sahai, and Waters, and Bonnet et al., we can actually take the commitments to the bits of x and derive from it a commitment to f of x. I'm not going to go into details of how this is done. This is just the standard FHE machinery that has been characteristic of many lattice-based constructions. But the takeaway is, if I give you the commitments to x that satisfy this relation, I can derive from it a commitment to f of x. So in a GVW construction, the commitments themselves are actually not short. Namely, I have one commitment for every bit of x. And the commitments are basically independent, and as such, this is not quite a functional commitment. So how do we get to a succinct commitment? So the approach that we take in our work is we're going to compress all of these GVW commitments into a single matrix C hat. The way that we're going to do that is we're going to just define Ci to be a simple relation on the C hats. So namely, it will be Wi inverse times G times C hat, where the Wi's are now part of the common reference string. So why we do this will hopefully become clear very shortly. So we're going to choose the commitment to be C hat. We'll set Ci to be W inverse times G times C hat. So let's just make this substitution to our main GVW homomorphic commitment. All I've done is I've substituted for the Ci's. And now I'm going to multiply both sides of these relations by Wi. So the Wi inverses cancel out, and I end up with a linear system. And this linear system, if you stare at it, looks remarkably similar to the linear system I wrote down for the vector commitment scheme, except the matrices A1 up to AL are now not uniform random matrices, they're now structured matrices. So what do we do to construct a functional commitment? We're going to do exactly as we did for our vector commitments. We're going to give out a trapdoor for the matrix B sub L and publish that as part of the CRS. Now, to commit, you basically form the target on the right, use your trapdoor to jointly sample the openings and the commitment, and now you have a GVW commitment to X, and you can do homomorphic computation and openings exactly as before. The security of this assumption now follows from the basis assumption, except we have a structured matrix rather than a random matrix. So this is a new assumption that we introduce in this work, that SIS is hard with respect to the matrix A, even if I give you a trapdoor for this related matrix, BL. This is a new falsifiable assumption. I view it as a Q-type generalization of the standard SIS assumption. As far as we know, this does not reduce to SIS. And this is a fascinating open question to try and understand whether this assumption holds under the standard SIS assumption. I'll note that the trivial case of L equals 1 does hold under SIS. But for L bigger than 1, we don't know. So there are several extensions that I won't have time to go into, but basically our functional commitment has several appealing properties due to its algebraic structure. For instance, for linear functions, you can actually support fast verification or preprocessed verification, and we can also aggregate. So you can have commitments and openings to many different functions. You can actually aggregate them into a single short commitment. Again, this relies on the algebraic structure of our construction. So to summarize, in this talk, I presented a new methodology for building lattice-based commitments. Essentially, the framework that we define is we start with the main verification relation, write down the linear system, and then publish a trapdoor defined by this linear system. The security analysis, in turn, will rely on the hardness of the short integer solutions problem, even given this related trapdoor. In some cases, this variant of the assumption can be based on a standard SIS assumption. In other cases, it doesn't, but it gives us much stronger functionality, namely functional commitments for general functions. So I think I've ran out of time, so let me just list a bunch of open questions. So part of it is analyzing the basis assumptions, formulating stronger versions of the assumptions that allow us to get better security or stronger properties. Can we get schemes with shorter CRS? Can we get schemes for opening to many different components of a vector with strong binding properties? And with that, I'll conclude. Thank you very much.
Thank you very much for the great talk. Since there's only 2 talks in this session, I think we can afford some questions, if there are.
Hello, thank you for the very nice talk. I see that one of the open questions is actually one of the questions that I wanted to ask about sub-vector commitments. Mm-hmm. So if your functional commitments is like general purpose for bounded depth circuits, could it be like applied to directly have sub-vector commitments based on this structured basis assumption, or?
Yeah, that's a great question. So the issue actually comes up in the definition of security for sub-vector commitments. So in sub-vector commitments, there's actually a consistency requirement. So for instance, let's say I'm opening to 2 different subsets that both have a non-empty intersection. It should be the case that the value for those elements in the intersection are actually consistent in the 2 openings. Yeah. Notice that for the binding property for functional commitments just says that for each function, there's only 1 value I can associate with it, but those values do not have to be consistent. So because we don't have this consistency property, the current functional commitments we have do not imply the stronger notion of subvector commitments, at least as far as consistency is concerned.
I see. Thank you.
Mm-hmm. Are there any other questions?
Yes, I have a related questions. I wanted to ask if you consider this stronger functional binding property. What are the challenges and why you cannot achieve it right now?
Yeah, that's also a great question. So this goes down to the second open question I wrote down on a slide, which is if you want a stronger version of binding, which I usually refer to as soundness or knowledge extraction, basically, that would actually give you a snark. So we would not be able to build it from falsifiable assumptions in light of the Gentry-Wicks separation. But one thing that you can potentially do is you can try to formulate a stronger knowledge version of these assumptions. This was done in the Albrecht et al. Work from Crypto last year. So you can write down these assumptions and try and analyze it and prove security. It turns out, though, that formulating a reasonable knowledge assumption that's not broken turns out to be challenging with the machinery we have. I think it's an excellent question, and I think for the constructions that I described here, it's not clear that there's an attack, but we also don't have an assumption that we can prove security from.
So one more question, yes?
Sorry. I just have a quick follow-up, maybe more on your intuition, whether we could have lattice-based subvector commitments based on like standard assumptions like SIS. Like you have this vector commitments with just 1 position opening, and it relies on this basis assumption which you reduce from SIS. So is your intuition that we could have such a subvector commitments based on those standard assumption, or do we need like more assumption and more complicated assumption like the ISIS F that was presented yesterday, or this structured basis assumption?
It's a great question. So I see no barriers. So I don't think there's any reason why we can't not do it from just plain SIS. I think right now the techniques we have don't seem sufficient, but there's always potentially new ideas or new approaches that would allow us to get better subvector commitments and functional commitments from standard lattice assumptions.
Okay, thank you.
So let's have all further questions offline, and thank the speaker again. So the second talk in this session on lattice constructions is called Efficient Laconic Cryptography from Learning with Errors. It is joint work by Nico Döttling, Dimitris Kolonelos, Russell W.F. Lai, John Wei Lin, Giulio Malavolta, and Ahmad Reza Rahimi. And Russell will give the talk.
Thank you for the introduction. I would very much like to talk about functional commitments and vector commitments here, but I'm also happy to talk about Laconic cryptography from learning with errors. So maybe after this talk, my goal is to convince you that Laconic cryptography is not just something that you'll see in crypto and Eurocrypt, but maybe in 1 or 2 years also in practical venues like CCS, okay? So, yeah, so I'm first going to explain what Laconic cryptography is, and then I'll talk about how we can build it efficiently from just the standard LWE assumption. Okay, so our context is the round optimal two-party computation. So here we have 2 parties, Alice and Bob. Alice, we will call Alice the receiver because she is the one who receives the final output of the computation, and Bob is a sender. So very generically, Alice and Bob, they both know some function f, and Alice has an input x, Bob has an input y, and Alice sends some kind of encoding of x to Bob, and Bob replies with some kind of encoding of y to Alice, and then somehow Alice can derive f of x, okay? So by some magic 2PC protocol. And for security, sometimes we require that Alice should not learn anything about y. So she only learns about f of xy, but nothing else about y. And sometimes we want Bob to learn nothing about x, or sometimes both. And in general, although here I talk about Alice and Bob, but there could be many Alices, so Alice could be one member of a big group, and Bob could also be one member of a big group. All right, so there is one very popular flavor of 2PC, which is informally known as Alice optimized 2PC. So in this setting, we want the work of Alice, the computational cost of Alice, to be very, very small, so only proportional to her input x, and Bob will do all the job. And this is kind of canonically solved by fully homomorphic encryption, which allows you to perform arbitrary computation over encrypted data. So very briefly, how would you do it? So first, Alice samples some FHE key pair, public, PK and SK, and she encrypts her input X under PK and sends both the public key and the ciphertext to Bob, and then Bob just homomorphically evaluates F and get a ciphertext of f of xy and send this ciphertext back to Alice. And then Alice just decrypts, right? So as you can see, the work of Alice only depends on her input x, but not the computation f. And that's why we say that these kind of protocols are Alice optimized. And this can be done nowadays with very efficient FHE, thanks to all these recent advances from fairly standard lattice-based assumptions. So you may still need super polynomial modulus or something like that, but it's quite standard. Okay, so Laconic cryptography is sort of a dual notion of Alice optimized 2PC, and for this reason, it is called Bob optimized 2PC. And it is an emerging paradigm with numerous theoretical results, but today I will show you that there will also be practical results as well in this domain. So the setting is as follows. Alice will, as usual, send some encoding of x to Bob. But now Bob, instead of doing some computation, he just encodes his input y and send this encoding y somehow to Alice. And then Alice will do all the work and compute f of xy. So again, we say that such protocols are Bob optimized because Bob's work only depends on y, and Alice does all the computations. So why is this challenging? Well, because Bob doesn't even have time to read f or x in full. So I'm cheating a bit here because I say that Bob inputs f. So like if you think of the circuit model, then Bob should read f in full. But let's say Bob gets some kind of digest or f, or Bob is a random access machine. So yeah, let's not care about that too much. But in short, Bob has not enough time to read x, and then also Bob needs to come up with some encoding of y so that it is just enough for Alice to unpack f of xy, but learn nothing else about y. So this is why this setting is challenging. So before telling you about the constructions, let me tease you a bit about the applications of Laconic cryptography to non-Laconic cryptography. So here applications for applications, I mean it in quite a broad sense. So it also covers the techniques that are used to construct Laconic cryptography. So basically, it has implications to primitives like identity-based encryption, multi-party computation, Gabo circuits, trapdoor functions, I/O, and private information retrieval. And generally speaking, these techniques allow you to take some weak computational assumptions and let them punch above their weights, and then allow you to construct something stronger, which natural constructions wouldn't allow. So let us look at a few examples of Laconic cryptography. The simplest setting, the simplest primitive in this Laconic family of primitives is Laconic OT. So here, Alice has a big database, D, consists of n bits, and Bob's input is an index I and two messages, mu0 and mu1. And what Bob wants Alice to know is that if the ith bit of D is 0, then Alice should learn mu0, and if the ith bit of D is 1, then Alice should learn mu1. Another example would be Laconic private set intersection. So here Alice has a very big set, maybe it's the list of all her friends, and Bob has quite a small set B, and here Alice wants to learn the intersection between A and B. More generally, we have this notion of Laconic function evaluation, where Alice's input is a very complicated function G, and Bob's input is a short input Y, and Alice wants to learn G of Y. So another example with more semantic meaning is that of registration-based encryption. So here is an example where Alice is actually a lot of Alices instead of just one. So imagine you have a lot of users, each with their own ID, and they are registered somehow to a service, and we collect all these registered user IDs in the set R. And so Alice's input conceptually consists of the secret key of one particular Alice, SK of ID dagger, and then the collection of all the ID public key tuples. On the other hand, Bob's input is a special identity, ID star, and a message mu. And the functionality is such that if the two identities match, so ID dagger is equal to ID star, and also Alice's know the corresponding secret key for ID dagger, then she can learn the message mu, otherwise she learns nothing. Okay? And this functionality also captures the so-called Laconic encryption that we introduced in this work, but more on that later. So before our work, all of the above, all the constructions of the above require so-called non-black box techniques, so using cryptographic primitives in a non-black box way. So to give you a concrete example, it involves something like homomorphically evaluating a circuit, implementing a public key encryption scheme, or running a Gabo circuit, again, with a circuit that implements a public key encryption scheme. And as you may imagine, this is completely impractical. So here comes our result. So in this work, we introduced the notion of Laconic encryption, which we think is arguably the simplest building block that you can have in Laconic cryptography, and then it implies a lot of other Laconic primitives as we will see. So for those of you who know about registration-based encryption, then Laconic encryption is basically the same as registration-based encryption, but without all those stringent update efficiency requirements. So it's a simpler version than registration-based encryption. And in this work, after introducing the notion of Laconic encryption, we provide a fully algebraic construction of Laconic encryption from the standard learning with error assumptions with polynomial modulus to noise ratio. And then we show that there are black box transformations from Laconic encryption to most of the other Laconic primitives, including Laconic OT, Laconic PSI, and registration-based encryption. But notably, we cannot get a Laconic function evaluation in a black box way, so that's an open problem. And also, for the first time, we implemented anything Laconic at all. So we provide an open source implementation of this Laconic encryption primitive. And so for a database size of at most 2 to the 50 identities, that is just a fancy way of saying that the identities are 50-bit strings. So if we encrypt with respect to such a database, then we manage to get encryption and decryption time at around 10 microsecond. Okay, and as a byproduct, using our techniques, we can also get identity-based encryption with unbounded identity space and tight reduction from learning with errors. So this might be of independent interest. So for the interest of time, today I'm only going to talk about the notion of Laconic encryption and also the construction from LWE. So first I must say that the notion of Laconic encryption actually existed in the literature implicitly, for example, in the existing Laconic OT constructions. So for simplicity, let us just consider the setting where we have a static array of public keys, pk1 to pkn, instead of with different identities. So here, imagine we have a lot of users with their respective public keys, pk1 to pkn, and they register at some service provider, and this service provider will hash all their public keys into a short digest, which is available to anyone, including Bob. So Bob just looks at this digest, and then using the Laconic encryption, he can encrypt with respect to a particular ID of his choice and a message mu, and send this ciphertext to Alice. Now, on the other hand, Alice can derive a membership witness of the statement that her public key is registered in this digest. And then using both her secret key and the witness, she can decrypt this ciphertext sent by Bob and obtain the message mu. For efficiency, we require that both the encryption algorithm and the decryption algorithm run in time much, much smaller than n, so sublinear in n, and actually we achieve polylog n efficiency. And for security, we require that the ciphertext, if you don't know the secret key for ID, then the ciphertext hides both the identity and the message. And actually, we prove that it is pseudorandom if you don't know the secret key. So our approach is very natural. So first, you pick your favorite public key encryption scheme, and then you design a so-called encryption-friendly hash function so that you can encrypt with respect to the statement that the public key ID is a member of the digest. So that, and the corresponding witness would be the secret key and the membership proof. Okay, so, but this is easier said than done. And so first we need to pick an encryption scheme, and then next we need to design an encryption-friendly hash function. So in lattice-based crypto, there are not so many encryption schemes that one could pick. So the favorite choice of everyone seems to be the dual regf encryption scheme. So in short, in the dual regf encryption scheme, you have a public parameter, which is the matrix B, and then the public key and the secret key are SIS solutions and SIS pre-image and image with respect to B, respectively. Or in other words, the secret key X satisfies BX equals Y and X is short. So next, we will design an encryption-friendly hash function so that when you concatenate, so the membership witness takes the form of the vector, and when you concatenate it with a SIS solution, which is the secret key of the user, then it satisfies a specially crafted SIS relation, where the matrix B corresponds to the matrix B is induced by the hash function and the identity, and the image is induced by the digest. And then once we have this, we can just use the dual regf encryption scheme to encrypt with respect to this particular SIS instance. So for those of you that are not familiar with dual regf encryption, let me quickly recap what it is. So again, the public parameters consist of a very wide matrix B, uniformly random, and the public key is an image vector Y, and the corresponding secret key is a vector X, a short vector X satisfying BX equals Y. Now, to encrypt under this public key Y, what do? You sample a random LWE secret S, and you compute SB plus noise. That gives you the first ciphertext component, C0. And the other component is SY plus some error-correcting code encoding of mu plus some other noise. And using the SYS solution X, you can linearly combine the two ciphertext components and recover the error-correcting code and encoding of mu plus some noise. But because it is an error-correcting code, you can decode it and recover mu. So the pseudo-randomness of the ciphertext comes almost immediately from the LWE assumption after some hybrids. So essentially, the LWE assumption says that the LWE with respect to the concatenation of B and Y is pseudo-random. And that immediately says that the ciphertext is pseudo-random. So, but the take-home message is that there exists an encryption scheme where the public key, together with the public parameter, is a SYS instance, and the corresponding decryption key is a SYS solution. So that's the most important message. Next, I would like to design, or tell you our encryption-friendly hash function. And for this, I need to recall the notion of gadget matrix, which David also introduced. So the gadget matrix G is a block diagonal matrix where each block consists of powers of 2. And the nice thing about this gadget matrix is that if you take any vector V and write down its binary decomposition, denoted by this G inverse operator, and then when you multiply G to the binary decomposition of V, you get back V. So how do we interpret this? So one way to interpret it is that although the bit decomposition operator is highly nonlinear, so like if you compute it in the forward direction, it's highly nonlinear, but when you just want to verify it, it's actually a linear relation because G times G inverse of V is a linear operation. So basically, we will exploit this fact and design our encryption-friendly hash function. So this is essentially the most important equation in the entire paper and also this talk. So, and this is our hash function. So this hash function takes as input two vectors, V0 and V1. And we first binary decompose the two vectors into G inverse of V0 and G inverse of V1. And then we take the negative, and then we perform a linear combination with coefficients A0 and A1. So if you pack A0 and A1 together horizontally, you can write it in this compact form. Now let us look at what happens when we use this particular hash function to build a Merkle tree, which hashes all our public keys. So here I'm doing nothing fancy. I basically pack all the public keys at the leaves, and then I compute the Merkle hash until I reach a digest, which is a vector denoted by Y epsilon. So as you may know, if you have a Merkle tree hash, then the membership opening is just the root to leaf path of the labels together with its siblings. So similar things are happening here. So if we for example, if we want to verify that PK01 is in the digest, then we collect all these labels, W0, W1, W00, and W01, and we concatenate it with the secret key of Y01. And we notice that this vector satisfies this particular SYS relation, where on the left-hand side we have a matrix which depends on the identity string 01 in a particular way. And on the right-hand side, we have this vector consisting of the root label Y epsilon concatenated with all zeros. So once we have this, we just use dual regF encryption to encrypt with respect to this SYS relation. Now, putting everything together, recall that there are many users with their respective public keys, and when they register, you hash the service provider hash all of them into a Merkle hash digest Y epsilon, and then everyone that is registered can compute its own membership proof by looking at the labels of this Merkle hash tree. So for example, the witness for the identity string 01 is of this form. And to encrypt with respect to a particular ID, you craft a special cis relation where the matrix B is programmed like this. So here, ID bar stands for the negation of the bit. So for example, if the first bit of the ID is 1, then you have 1 times G here and 0 times G here. So that means G is put under A1 and 0 is put under A0. And if the first bit is 0, then it's the other way around. And you do this for every bit in the identity string. And as I said, the image of this cis relation is just Y epsilon concatenated with all 0. So now the encryptor just encrypts with respect to this cis relation. And naturally, the decryptor can use the concatenation of the witness, membership witness and its own secret key to decrypt. And correctness just follows naturally. So next, let me talk about some key points in the security proof. So note that we cannot use the security of dual regF encryption directly because this specially crafted cis relation is not a properly distributed dual regF public key. So to argue security, we actually need to be very careful and analyze analyze LWE with respect to this very structured matrix. But nevertheless, we can peel off these rows of this matrix one by one until we can reduce everything from LWE. So, but as usual, like if you have done this sort of proofs before, you realize that somewhere in your proof there will be, so you define some hybrid experiments, and then in some of these hybrids, you would have some linearly correlated LWE samples. And then in the next hybrid, you will have short linear combinations of some fresh LWE samples plus some fresh noise. And you would like to argue that these two hybrids are indistinguishable. And so traditionally, these sort of things are done in two ways. So either you assume a super polynomial size modulus, and then you use this so-called noise flooding, drowning, or smudging technique, however you want to call it. And then you can actually show that these two distributions are close statistically, but this would require using a super polynomial modulus. Another approach is to argue about the Renyi divergence between these two distributions, but this will incur polynomial reduction loss. So in this paper, we actually show that these two distributions are computationally close by the LWE assumption. And we call this new assumption the error leakage LWE assumption, and then we prove that this assumption just holds from assuming standard LWE. So we believe that this lemma is of independent interest. So to conclude, in this paper, we provide the first fully algebraic construction of Laconic encryption from standard LWE, and we provide black box transformations from Laconic encryption to many other Laconic primitives, including Laconic OT, Laconic PSI, and registration-based encryption. And for the first time, we have an implementation of anything Laconic, and the encryption and decryption time are fairly fast. And we also have some implications for identity-based encryption. So yeah, thank you very much.
Thank you very much for the great talk. Are there any questions? Yeah, otherwise, maybe I would ask a very brief one, since it's the last one, and maybe have an outlook to future. Do you see further applications of Laconic encryption?
So you mean further applications other than what is implied here?
It's an open question. I don't know.
Okay, to be honest, I don't know. I mean, so there is a lot of space for tweaking parameters, and then they may fit different practical applications, because all these current implications that we have are at the primitive level. But for applications, so one primitive could have implications in many practical applications. So yeah, it's not a satisfactory answer, sorry.
Well, but thanks a lot. So thank you very much for attending Eurocrypt, and in particular this session, and have a safe travel back.
question.